Hi there, guys. I'm Chris Bowden, and you're not.
And I'm Paul Kidwell.
Welcome to the Geek Group, deep under Cayenne Mountain in the basement of the Science Building. We're here once again.
And our sinuses are clear.
Well, you're melting, so everything on you is clear. You're just blasting like 5 liters a minute here in August. We're in a basement, and you're still melting.
Yes, it's very warm.
I'm glad you lost
It's not so
150
much,
pounds.
it's the humidity is just nasty.
All right, so we're back again.
Yes.
And we're doing, this is Electronics 101 stuff.
Yes.
And today we're talking about what? What's the thing here? Because we've learned the basics with the oscilloscopes.
Yes, and we're going to use it a little bit to delve into this little thing we did on the whiteboard here.
Oh, the viewer mail.
Yes,
from the Uzbekistan kid.
Yes. The transformer he had was a 3,000 volt center tapped transformer where the center tap was tied to ground.
Yeah, it was like a 30 milliamp NST.
Exactly. Well, we drew nice, pretty pictures and tried explaining things, but I dug out a transformer for us to do an actual hands-on, let's show exactly what's going on and why sort of thing.
Okay.
All right.
And I noticed the transformer you dug out, we'll let him zoom in there a second. The transformer you actually dug out is an Archer brand transformer.
Yes, where's the name? It's on here somewhere. Let's say model 2731511A, made in Taiwan. There it is. Archer. There we go.
Now, for the old school geeks out there, they'll remember that's the original Radio Shack brand.
Yes, back when Radio Shack really was a
back before Radio Shack sucked.
When they were a good electronics store. I mean, you could go buy anything there.
Yeah, if you have any need to get electronics in the Grand Rapids area, don't go to Radio Shack. If you need a brick and mortar place to get stuff like this in the Grand Rapids area, you want to check out SF Electronics over on Leonard. Oh my God!
You got to take me.
Oh, I'm taking you there. Oh yeah.
Yeah.
Oh wow.
Are they open on weekends?
I have no idea, but we'll find out.
Yes.
You get out on a weekday, and we'll. Oh.
Okay.
Oh, they're cool.
Anyway, continuing on. This is a 120 volt, 60 hertz primary, and on the other side, they tell us that it is a.
That's plugged in right now, isn't it?
Yes, it is. That's why I'm being careful. It's 6.3-0-6.3. And what
so it's...
What
it means you ain't got to be that careful.
This is our center tap. If you ground that, you got 6.3 volts from here to here.
At what current?
Well, they're saying it's rated at 3 amps.
Oh, so it's pretty wheedly.
Yes. And you also have 6.3 from here to here. And you'd have 12.6 from there to there.
Okay.
Now
why would you want 12.6?
That's RMS voltage. Okay. When you rectify it and throw a filter cap on it, you're going to wind up with a different voltage.
Yeah, but would you get exactly 12? Like,
no,
do they add up so that...
You'd wind up getting slightly more, but then you're going to want to put a voltage regulator on it and regulate it down.
Okay.
So your input to your regulation needs to be higher than the voltage you want when you're done.
Okay. So they give you a little bit more just to end up in a nice happy space.
Okay. Now, I have a Fluke Model 112.
Here, I'll get a close-up on that.
True RMS.
Right there. See it?
Multimeter.
Okay. That's my meter.
That's your meter, yes. I grabbed it out of the toolkit.
It's my
and I
meter.
Cleaned off your probes. They were
What's wrong with my probe?
I scratched the tarnish off. They were like nasty.
It's hard being me, man.
Anyhow, this is an auto-ranging meter. So if we set it to AC volts, we don't have to worry about what scale we set it to.
Show them there. You can zoom in.
Okay. I've set it to AC volts, and the scale will auto-adjust based on the voltage I put into it. So
when you use an auto-ranging meter, you have to pay close attention to more than just the numbers so that you know where you're at.
All right. Now, I'm going to go from our center tap to one side.
And we should get half voltage.
And half voltage. We're winding up with about 6.6. the reading we're getting, we're going to put it on the oscilloscope in a minute so we actually see the peak voltage that we're reading and stuff like that.
And with the oscope, we can put in both sides of the transformer and show the phase relationship between the two. I like that idea. That's cool.
Because right now you read 6.59 there, and you get 6.59 over here.
And if you go between the two, you'll get 12 and change.
You'll get, just 13.2 roughly.
Cool.
Okay, now we're going to come up to our scope right now.
Yes.
And let's see.
Now we don't need the whiz-bang digital storage for all this, but it's here.
It's here, we use it. All right, I'm using a ×1 probe instead of the ×10 probe.
Yeah, this is your $5 probe.
Yes.
I'm going to get rid of the wad of cables that you've got.
So I'm going to set it on 1 volt per division, and we'll figure out the time in a second. And quit poking me.
I'm just seeing if
we're doing line triggering, so I can set our 0. We're going to be playing with AC, so I'm going to put the 0 right at the middle.
Okay.
Like that. And I'm going to start clipping on. All right, I'm going to clip our ground on ground.
You're going to need that.
And yeah, that would work better, wouldn't it?
Yeah, it would. And
I'm going to use that one.
Well, you're going to need both.
Well, give me a minute. Well, okay. Eventually.
Well, you're going to need a ground somewhere.
Okay.
Now, do these
I'm going to tie their center tap to the actual ground line.
Okay. Now, hang on a second. Do the two channels on the scope share a common ground?
Yes, they do.
Okay, then I have an idea. Watch this. Now, this is grounded to here, right?
Yes.
Okay. Take this, put it in channel 2.
We're going to be using channel 2 in a minute.
Yeah, I know. But, watch this. Take that and grab your signal. Okay. Mm-hmm. You can ground this out on the mess you've got there, and then that can come over there, and then you've got both, and you're set with just those probes. Now, you don't have to use any of the pokey probes. You can use the clippy probes.
We're going to be changing a couple of things. I'm not using for the pokey probes.
Okay.
We're going to be changing a couple of things around here. Okay.
You got a whole lot of something happening there,
We
Paul.
got a whole lot of something. I need to turn my voltage down.
A little bit.
And my time down. There. Now, AC...
That's an ugly waveform.
That's what AC coming out of the wall looks like.
Really?
Yep.
It's that bad?
It's that bad. Okay, I'm on 5 volts per division. We'll set our voltages the same.
There's a commercial for APC if ever there was one.
Now, when our voltmeter read 6.8 volts, that was the RMS reading of the voltage.
Okay.
Which, to calculate your RMS, you multiply your peak voltage times 0.707, which is...
Now, hang on. I'm looking at the picture on the scope here.
Yeah.
And from there to 0, that should be our voltage, right?
Yeah.
Okay, from 0.
That's the peak voltage.
That's the voltage. That's the voltage is the voltage. The top of the thing is the voltage. What's the difference between peak voltage and root mean square voltage, or RMS voltage?
Well, that's what okay. The RMS, root mean square, it's like the average voltage over time. The voltage we're seeing here, at one time it's 1 voltage, at another time it's 0, and then it goes negative. So the voltage we're reading at any instant isn't necessarily the 6.3 we're seeing on the meter, because the meter does an average over time as well.
Now, when do you actually need to know that? Because, I mean, for everything I've ever done, if you plug something in the wall, you need to know, is it 110 volt or is it 240 volts?
Okay.
That's pretty much all you need to know. When do you need to know this RMS versus peak?
When every voltage that you're seeing, when they're talking like that, they're talking RMS voltage. It's the equivalent voltage as if it were a DC circuit.
Okay.
So when you're calculating things like wattage and stuff like that, the voltage that you plug in is the RMS voltage. A lot of the, they don't do it anymore so much, but a long time ago when people were selling speakers and whatnot, they would tell you what the peak wattage of your speaker is.
Yeah.
Or the peak-to-peak wattage.
There was RMS, max, and then the third one that I invented for dealing with stereo store guys was the ILS.
ILS?
Yeah, you have a set of speakers that were like 200 watts RMS, and they're 400 watts peak, but they're 500 watts ILS.
What's ILS?
If lightning strikes.
If lightning strikes. Oh, that's bad. All right. 200 watts peak to peak.
Okay.
Sounds like a lot. Well, that's going from peak to peak.
Okay.
Well,
there's a whole lot of things in the middle there.
There's a whole lot of
nothing.
There's a whole lot of nothing in the middle. If you rectify that, so you're only looking at your voltage relative to ground, that's only 100 watts peak. But it's still got that sine wave in there, and there's a lot of stuff that's below, you're not at this peak voltage, you're down here near zero. That's where RMS comes in, because basically it takes that wave and flattens it out into a DC signal so you can get the equivalent to what it actually is.
Okay.
And for a pure sine wave, which obviously we don't really have
We're trying.
But for a nice pure sine wave, the average voltage is like 0.63 times whatever your peak is.
Okay.
Your equivalent voltage, your RMS voltage, is 0.707 times your peak voltage.
Okay.
So from that 200 watt peak to peak stereo that you were buying, it's actually 100 watts peak, and that means it's 70.07 or 70.7 RMS.
Now, I'm curious, well, we've got this all set up. I'm really curious, and we should do this in one of our upcoming videos, of exploring raw wall power by like taking an O-scope, not this one where it's a stationary image, but one of the analog scopes, and hooking it directly into the wall. Will they handle that? Can they handle that high a voltage? Like wall voltage, I don't know what this will go up to, but wall voltage, you figure 110 volts.
Let's see.
Because if we could do that, it would be neat to see the wall power with... I want to see all the noise and the guns and see just how bad it is in real time.
This will go 50 volts per division. I mean, you can use this to probe a... there's your analog right there.
That's the wall.
That's coming out of a transformer. You could plug this into the wall.
Okay, well, going through the transformer itself cleans up a lot of the high frequency transients, any high frequency noise in that, just from the inductance in the transformer.
Anyhow, let's go a little farther here.
Okay.
All right, I've used my cursors again here.
And they're moving.
They're a little bit.
You're drifting, Paul.
But I have one cursor on our zero line.
Okay.
The other cursor is at the bottom here, and it's reading 8.4 volts. That's the peak voltage reading. If I put this one, so now I'm going from peak to peak, I'm reading 18 volts.
Okay.
All right. Now,
which is totally different than the numbers you're getting.
Totally different than the numbers.
So this is peak, that was RMS.
This is right now we're at peak to peak.
Okay.
This, it says right on it, true RMS meter.
Yes.
So that is an RMS meter. That's.
So does that mean the meter itself is doing math?
Like the meter itself is doing math.
Okay.
Yeah, I'm showing 6.6.
All right, let's look over here. Let's make sure we can see it. Okay, there you go.
There, I got 6.6 there with 18 volts peak to peak.
Okay, so you got 6 volts there, but you got 18 here. So this is 3 times that.
Well, again, it's what you're actually measuring.
Yeah, but 3 times difference?
Yeah.
Wow.
Like I said, those guys selling stereos were... All right, we get to do a couple of things. Oh, let's take next little step here. I'm going to ground. Now, he wanted to ground one side of his transformer.
Well, his goal was to have a 1-wire output with 3,000 volts.
Okay. I'm disconnecting our center tap completely, so it's not going to touch anything.
I don't think he understood that the 2 wires on his transformer were out of phase with each other.
We'll get to that in a sec.
Okay.
I'm going to ground one side of our transformer, and then pick up the other side here
Oh, wow.
Don't let that touch. And you can see we got
35 volts.
Yes, and our cursors are still in the right spot.
Yeah. Well, we got 36 volts now.
We got 36 volts peak to peak.
I'm guessing the case of our transformer is floating?
The case of right now, yes, the case of the transformer is floating. That's about the 0 line there, so we have about 16 volts
now,
peak voltage.
And an important thing to understand here, when I say like the case of the transformer is floating, what you need to understand is how voltage works. Voltage is a measurement of potential difference. Voltage is a meaningless number, but voltage is when you're measuring voltage, you have to have voltage relative to something. It's like decibels.
Yes.
It's always like, decibels per watt or whatever. Volts is the same thing. Now, characteristically, when people talk about volts, they mean volts in relationship to ground. So if you look at a wall plug, toss me an extension cord. Just give me a outlet strip or something. Okay. Now, let's say this is your wall outlet right here, and I'll turn this so it's right side up for everybody in the United States. Now, we're here in the US where our wall outlets look like this, and it's the little smiley face. I need a probe. Give me a probe for just showing
point with
people.
that.
Okay. Now, when you're looking at a wall outlet in the United States, a modern day one, they all have 3 holes. There's a big hole, a little hole, and the bottom round hole. Now, the little hole here is the important one. The other 2 you don't have to worry about. The big hole and the round hole, safe. This one here, that's the hot lead. Okay, this hole behind it has 110 or 120 volts or whatever, but it's between 110 and 120 volts. Around here it's like 117, I think is standard. Now, this is the hot lead, the black wire. On this side, the bigger straight hole is the neutral lead. This is the grounded conductor. Down here is the ground lead. This is the grounding conductor. So we have the black wire for the hot, the white wire for the neutral over here, and the green wire for the ground. Sometimes it's yellow, but yeah. Now, when they talk about 110 volts, they mean that between here and here is 110 volts. Between here and here, you should also get 110 volts. And if everything's going really well between here and here, you should ideally have 0 volts, but sometimes neutral will float a bit.
If you have a heavy load, you're going to get a voltage drop across your neutral line between your connection point here and the breaker panel.
But I don't want to get into that kind of heavy stuff. But
the ground is tied to ground. The grounding conductor is tied to the neutral.
This is tied directly
at the breaker panel.
Yes,
that's the fan out point.
Yep. And we'll do a whole thing on grounded conductors versus grounding conductors. But what I want you to understand is right here you have 110 volts between here and here. Now, when we look at, if you look in your breaker box, you've got 2 rows of breakers. Now, the power feed to your house, there's no wire to your house that is more than 110 volts. There just isn't. There's 3 wires that feed your house, and there's 110 volts between this wire and here. The middle wire is neutral, or ground. So between these 2 wires, you get 110 volts. Between these 2 wires, you get 110 volts. You have 2 hot leads and a neutral. But that's relative to ground. Now, if you throw ground away, and these 2 wires are out of phase with each other, from here to here, since when this one's high, this one's low, okay, so these wires look like that. Between these 2 wires, the relative voltage is 240 volts. So you've got your 110, 110, 240, and that's how you can get 240 volt outlets in your house for like an electric dryer or something like that, even though you only have 120 volts coming into the house. You can do that because they're out of phase.
Okay.
And his transformer works the same way.
That's right. I have 3 wires, 2 reds and a black.
I can get into a lot of other stuff with the floating there. I was going to talk about filament transformers and X-ray transformers.
Yeah, if you want to do that right now, we can do that.
It's a quickie, so let's cover that so that people,
Okay,
because that's a perfect floating transformer.
All right, you do that. I'm going to change some wiring around here so we're showing something a little different.
Okay, you rock out on this, and I'm just going to try and give people an introduction to this. All right, in an X-ray transformer, which you've seen us play with in a lot of videos in the past, there's actually more than one transformer. You have to have a very high current but very low voltage power supply that feeds out for the filament in the X-ray thing, in the actual tube. Now, the wires that are feeding this transformer, that feed this tube, the tube is insulated at like 150,000 volts. So they only need 3 volts, like 3 or 6 volts. It's really tiny, but at some serious amps to feed that little filament in there. So what they have is a transformer inside the big main X-ray transformer case that this little transformer only outputs like a 3 volt difference. So the transformer is at 150,003 volts for this little tiny block transformer. And that is, when it feeds out to the tube sees 150,000 volts, but the little filament inside it only sees 3 volts because it's floated up. So the whole transformer is floated up, where the transformer itself is 150,000 volts relative to ground, but it's only 3 volts relative to its own power supply. So that's how voltage can be relative. It all depends on where you see it, where you're measuring from and to. You need 2 numbers for your voltage, or 2 references.
I got something to show you.
What you got, Paul?
Okay. There's channel 1. It's showing one of our red wires over here.
Okay, that's one of the hot leads out of the thing.
Okay, here comes channel 2.
Whee! They're out of phase, Paul.
They're out of phase.
That's cool.
180 degrees out of phase.
Okay.
So when this wire is high, this wire up here is low.
Yes.
When this wire is high, this wire is low.
And this is a great way to show what I was talking about, because we can take a proby pokey thing like this right here. Now, can you, just out of curiosity, can you add a reference line down the middle here?
Unfortunately, no, I can't put a 3rd line in there.
Okay, well, you can see our crosshairs
Well, I can show you where 0 is. There's 0 for that one.
That's 0 for that channel.
And I put it right on one of the black lines.
Okay.
There's 0 for that channel.
Okay.
Would you like them laid over the top of each other?
No, because it actually makes better sense like this. What I wanted to do was show their AC. Never mind. I need that for a second. All right, here, we'll look at this probe. Now, you'll notice when I mentioned the voltage doubling between the 2 channels on the thing, you can have this, knock one of these down to 0. If you look at this, we've got our AC here, peak to peak, and then it's zeroed at the middle, okay? Now, this one's the same way. 0 for this would be right here in the middle. Or it could jump up. There we go. Okay. And so let's bring them both back so we've got our phase. Now, if you look at just one of these, and you're measuring relative to ground, and ground for each one of these channels is right here in the middle, you get your 6 volts or whatever it is.
There I'm on about 0 for both.
Okay. So our individual voltage of each channel is what, 8.6?
8.6.
Now, if we take and combine those 2 channels, we've gone from having to reach from here to here, which is a really small spot, to here all the way over to here. So we've just doubled our apparent voltage. And that's what I meant by you can hook the 2 things together. And it's the same thing with your house. This is exactly how your house is wired too, with 2 hot leads that are out of phase.
Okay.
So what you got there, Paul?
I got a little box.
You got a little box.
And I got...
What's in the box, Paul?
I have toys.
Looks like diodes. You wouldn't happen to have diodes, would you? 1Ns?
1N 4001 diodes.
Hey.
Now, we can't really run these are 1 amp diodes, so we can't run a lot of current through.
It's only a 3 amp power supply.
So what I'm going to do is we're going to build the diagram
We're going to show them.
What we have here, let's see, can we see here? There's a silver stripe at one end.
Here, aha, I've got a black box. Put it behind the black box.
Okay.
Ah, they still can't see it.
Well,
there.
light them up.
That sucks.
That's
all right, there's
all right.
a silver stripe on a diode.
The silver stripe corresponds to the stripe on the diagram.
Okay.
So what I'm going to do is I'm going to tie the 2 stripes together, and we're going to do a very high-tech method of tying them together. It's called twisting.
That's a rat tail splice. There's a technical term for that. It's red tail splice.
And now I'm going to take these two lines and tie them to the two red wires.
Now, hang on. On these two diodes, you've got both of the stripes on the end of the diodes, the polarity indicators, are pointing the same way. They're both at the bottom here.
Correct.
Okay.
Yes. So let me get down here and twist things together. I'm going to keep the ground on the center tap on the transformer, just like in our diagram up on the whiteboard.
Come this way a little so you're on it.
Is that better?
Well, watch your blocking. You can see where you're at.
Okay, and then this one is going to go here.
Love this high-tech assembly techniques here. And you got a breadboard right over there. We using it?
Well,
We're
this
just
has
gonna
got,
twist stuff
this is
together.
all stranded wire.
I know, I just like messing with you.
Okay, so now I'm going to take my scope lead and I'm going to put it on the center point of the diode.
Ooh, I see a rectified signal there.
So
And there's our zero line. So let's take this down to the zero.
okay, I'm going to get rid of channel 2.
Okay.
And then I'm going to let's ground it so I can position it.
Okay, now this is ground where we're moving it to.
I'm going to put ground in the middle just for the time being.
That's grounded there. So when we bring that back, now we're completely above ground. This is a positive signal, and it's humpy.
It's humpy.
Now
yes,
this looks a lot like if we had the whole waveform and folded the lower half above, like if we flipped it over.
That's effectively what we did.
Now what we've...
Okay, now I'm moving my cursors to get a measurement, and now we're showing roughly 8.4 volts
Okay.
peak voltage.
Now the reason we have 8.4 is, even if you look over there, you can see we've connected to both. But what the diodes do, a diode is a one-way valve. Think of it like a check valve. It lets electricity through one way, but not back the other. So when the voltage swings positive above zero, it'll let it pass through, but when it swings low and it tries to go backwards, it stops it. It locks it right off. So we've got both channels out of the transformer, both of our taps, and each of those is out of phase with each other like that.
Oh,
now
man.
we're cutting off everything, we're cutting off half of the energy coming out of there and throwing that away. Half of the voltage is gone. Everything below zero is gone. We're only keeping the upper part of the waveform, and we're taking the two upper part of the waveforms and summing those together. So where they'd be out of phase, now they're both boop, and we get doot, 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 and we get here. See, there it is. Doot, 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 doot. And you got to make the sound.
Yes.
It's like the old Bill Cosby thing with the
Okay.
marker. So that's how we get that.
To make a DC power supply, we have most of it taken care of now. You'd add a capacitor across ground and our diode output here, and that would take the tails off. Basically, your waveform would peak and then decay down, and then the next peak and decay down.
Now, do you happen to have another two of those?
Yes,
another two
I
diodes?
do.
Because we could show the difference between, because this is a half wave
No,
rectifier.
this is full wave rectification.
But you've only got two diodes.
But I only got two diodes because it's a center tap transformer. I'm grounding at the center tap.
Ah, okay.
Now, if I take two more diodes.
It won't really impact it at all.
Oh, wait a minute.
Okay.
This
Are you
is
going to
something-
unground it?
Now, oh, yes, I will.
Okay.
On these two, I'm going to take the end away from the stripe and twist
Okay.
them together.
And just for the people who have gotten to the point where they understand a schematic a little bit here, this is the signal for, or this is the schematic symbol for a diode. Now, if we take and put four of these together, we get the schematic symbol for what's called a full wave bridge rectifier. And that's what we're making right here. You can see Paul winding it together. But this symbol right here is a full wave bridge rectifier.
Yes,
And you can see if you
kind of a
look
diamond shape.
Yep, and if you see which way the arrows point, you can see which way the electricity flows.
All right. I haven't really done anything to our circuit by adding this right now. And as you can see on
Yeah, it's still exactly the same.
I'm going to change our 0 point here because things are going to happen in a second. I want to put 0 like down here at the bottom.
Okay, put it right on that line. There you
And we'll
go.
put it right on that line. All right, so there's our little humpies.
Okay, and we're completely positive above zero. We're making very
Now-
humpy DC.
You can do that with a center tapped transformer because you're grounding at the center tap.
Okay.
If you ignore the center tap and tie in your ground to the bottom two diodes on the full wave bridge rectifier,
Ooh, we got some more voltage there.
we got a higher voltage.
Now unplug that a second. Let's show the difference. There's before.
Well, whoa. Hey, we just melted our diodes.
A little bit.
The smell of burning silicon
It's
is
a very,
just
very
wonderful.
distinctive aroma.
And you'll notice we still have the.
Now, hang on. We got to show people. Paul has just. Oh, damn,
That's hot.
Yeah, hang on. Let me.
Hold
that's why
on.
we have Gerbers.
I got
it. Paul has just created right here. This is. I'll get up on this camera. You can see it. Paul has just created a pair of SEDs. These are smoke-emitting diodes, and are very common in the electronics world. Anybody who gets into hacking and tinkering with electronics on a workbench, you will make smoke-emitting diodes on a regular basis. So how did you do that? What did you do wrong here?
Let's see, what did I do?
Because you know there was 1,000 people around the world who saw when you clipped that on there who were like, oh, just wait, it's coming.
The problem is we're not current limited.
Ah, okay.
Okay. Actually, I think the problem is this ground connection over here, because my center tap was still grounded. I unclipped our scope, but we were still grounded.
Okay.
So I'm thinking we're going to try it again.
You want to try it again?
I want to try it again.
Hey, we haven't blown up enough stuff yet today. It's always a good time.
It's like I could sit here and spend the time and figure it all out.
Hey, I can spend all day burning stuff down with you. It's not like we've never done this before, and I'm just happy we're doing it with cheap stuff.
Yeah, diodes come in all sorts of sizes.
I remember the adventure of the relay.
You still have one of the big, huge ones floating around. I mean, floating around here. I mean, that was
not here. Not here.
Okay, I should have brought one.
All the big diodes are at the lab.
Like
We've got diodes as big as your fist.
I mean, they make an excellent set of brass knuckles. I mean, just huge. Like 150 amp rated.
Oh, we've got them way bigger than that, but yeah.
Okay. Now, it really looks like I got it oriented right. So at the
hang on. Do you want to cut out some of the pieces in the middle there before we confuse people?
Fine.
You got some extra crap in there, and these, we're doing this for people that may not be very familiar with this. So here, cut it out. Cut it out.
I just got this one little piece that needs cut. Actually, there, it's gone.
All right, because I care. I'm here to help. I'm trying to teach people.
Right. There is our full wave bridge rectifier.
Okay, and we have a funny.
All right, I got the stripes. The stripes are all on the top sides of the diodes as they're sitting there.
Okay.
So.
Clip that on there, and we've got huge.
Ooh, yes.
Yeah, we're way.
That's what I was expecting the first time.
Yeah, it didn't look
now,
right the first time.
Give me 1 second.
Okay.
Okay, we're not getting warm this time.
We're doing it right.
Okay. Yeah, the ground is what messed me up. I said we were going to get rid of the ground, and we didn't get rid of the ground.
Huge peaks.
Okay,
Huge peaks. We got 17 volts.
Yes. Okay. We're using both sides. We're using the full coil on the transformer on the output. When we, I'll go back to
the whiteboard.
We're going to the whiteboard.
All right. Let me make sure I'm out of your way. What do we got, Paul?
All right. There we go. I don't know if this is going to show up, but when we were doing AC, and we'll put 0 like right there. When your AC voltage was above 0, one diode would conduct, the other one wouldn't. So you're only using that much of the output.
Your electricity is flowing through here, not through here.
From ground through there out to your load.
Because this one's blocking it, because the
arrow
arrow points that way. So
when we proceed along and come down here, that one's blocking, that one's conducting. So again, you're only using half your coil.
Okay, so we're using both sides of the transformer, but not at the same time. We're using here, and then we're using here, and we're here, and then we're here, and it's one at a time.
Okay, yes. Okay. Now, we still don't have anything to erase with, do we?
What do you want to erase?
I want to erase from here over. And the diodes.
I worked hard for those diodes.
Okay, and get rid of this here too.
Get rid of it. Now I've got green Buki hands.
Now we're going to put in a full wave bridge. And it shows up as a diamond, and the stripes go at the top.
Yeah. Got a green hand, Paul. We gotta talk about
Hold
quality.
on.
Yeah, we really gotta
I
talk
just
about the
messed
quality
it.
control
Okay.
on your diodes there, Paul.
All right. I messed up.
Here.
Now I got a green
Hang on,
hand.
hang on.
Okay, that's fine, that's fine. Okay, that's good.
I'm here to help.
You're
Well,
here to
now you
help.
gotta dry it up.
I said
there you go.
the stripes go at the top, and that was, the stripes go at plus. Your
Plus?
your plus output, your positive output is going to be where the stripes
That
are.
would be the anode.
So I'm going to ground this side of our bridge, and the stripes go towards the positive side.
Okay, so this relates to the stripe on the diode.
Yes.
Okay. So this is the plus side. You sure about that?
Yep.
Okay.
And there is our output. Now, we're not going to get into electron versus hole flow. If I ever die and meet up with Mr. Benjamin Franklin, we're going to have words.
You and every other electrical engineer on the planet. Yeah.
Okay. If what it relates to is
No, we're
you're
not going to go there. We're not, because man, that's a fight. That's just. There's a whole video just for that.
okay.
There's a whole. I'm just going to walk away. I'm going to say, okay, we're rolling, and I'm going to walk away, and I'm going to let you scream for an hour about how it's been backwards for 200 years, and cool, fine.
Okay. Suffice to say,
They're doing it wrong and have been for forever.
it was a guess at the beginning.
It was?
Yes.
And he
It was
just-
arbitrary. They could have assigned it either way because at the time they didn't know.
Okay, and he just.
He picked wrong.
Okay. It's not my fault. I wasn't there.
Can I say one thing?
Go ahead.
If I have a glass of water and I have an empty glass, and I take the glass of water and I pour it into the empty glass, is it the same empty in this glass that used to be in this glass?
No.
No, it's not.
Okay.
Now, does it matter that it's not the same?
No.
Not really. But damn it, it's not the same empty.
Okay.
Anyhow, what it boils down to is, when current is flowing this way, you're going back and forth. So in one half of the wave, the current's flowing this way, and in the other half of the wave, the current's flowing that way. And I'm going to bring that down on top.
Don't anger
of
the
it.
dinosaur. Yeah.
When the current's flowing this way, we come into the top of our bridge. We're blocked one way, we can flow the other way. See, the arrow shows
yep.
the direction of flow. So current can flow there, go out to the world, and we're there meeting.
Now it's going out here and it's coming in here.
Hold on. We have a load to ground.
Okay.
I can't write
I'll
that.
write.
You're right, load.
Yeah.
All right.
Load.
There's a
Now,
load resistor.
since this goes to ground, this and this is connected.
Right.
So when it's going this way, it's
So
going
here,
out here.
there.
It's going down this side and hang on, down this side, and this is. Are
It's
you
gonna
sure
go-
we're right
yeah,
here?
yeah,
Because we've got to get.
it's going to come in
Because
here,
it's coming
go
in ground, so
down
it's
here.
going down both
Yeah, then
Okay.
it comes out and completes
and
the
completes a
circuit.
circuit. Okay,
Now.
so we're doing. Doo-doo-doo. It's down.
Right.
Now when it goes the other way,
When it's going
it's
flowing this
going
way,
out here,
it comes up, it goes
comes
out
in,
there,
and it goes up here.
and up there.
So it's always, electrons are always going this way, and then this way, and then this way, and then this way.
Don't say electrons, just say current.
The mighty force that moves through the ether is
Current is either it's flowing with the arrows.
Yes.
For one half of the wave, it flows like that. For one half of the wave, it flows like that.
But it's always moving through one of them.
It's always moving out here.
Took my cap.
There it is. All right, and that's what we've demonstrated. And I got it right now because we haven't burned up yet.
Yeah, it's still going, and there's you can see there's still lines on the scope, and life is good and happy.
Yes.
So okay, so that we've now solved the kid's problem.
All right, this is why if the case of his transformer is grounded, well, what just happened to us is what would happen.
Yeah, you'll burn it up. So
you'll burn
so
something
let
up.
us make the mistakes here with 6 volts on the bench than you doing it with 3,000 volts.
Yes, that would be
your
bad.
hand.
Now, you mentioned voltage doublers.
Yes.
And if we had our simulator thing set up,
Yeah, we'll get there.
we'll get there.
Do we have a couple capacitors?
Unfortunately, we don't. I didn't bring caps.
We got diodes. I mean, it's
I know.
trivial.
If we had some microwave oven caps floating around, but that's all back at the lab.
Okay.
So that's another video for next time.
Okay, cool. So that's it for this one. We've covered everything we need to. You guys, thank you for watching. Stay tuned. We'll have more. There's a whole series we're doing on everything you could ever want to know about electronics. We're starting very simple. It's going to get way more complicated from here.
We're going to add one step at a time.
In the next one, you can talk about hole versus flow versus electrons versus current.
That'll be a special one. The next one we'll throw a cap on here and show what happens when you filter this.
Okay.
And it's like you put a cap on, it'll smooth that out.
Okay.
You put a load, like a heavy load, close to the
It'll pull it
rating,
down.
and you'll start getting a ripple.
Yeah.
in
Well,
your
we've got
output.
a hell of a ripple.
We got a hell of a
We-
ripple right now. Well, that's one of the things they have a rating on a power supply.
Yeah,
when
it's
you get
ripple.
a wall wart is how clean is it, how
Yeah.
much ripple is in there based on how much you're drawing through. And we can show that with this scope.
Cool. All right. Well, thank you guys for watching. I'm Chris.
I'm Paul.
He's getting there.
I'm getting better.
He's getting in there. We're with the Geek Group. If you're not a member yet, you should be. Go to thegeekgroup.org, fill out a membership application. It's free, it's easy, like me, free and easy. You know you want it. Remember to rate, comment, and subscribe. Really, you don't need to rate or comment, but subscribe.
Subscribe,
because most of the YouTube commenters, we hate you guys. We really just...
Oh,
and
don't go.
love the viewers. Most of you commenters really need to die in a fire, but that's just me.
And is the white balance okay on this one?
Yeah, are you happy with this one? Are you? How's it sound? Really? Because we got a rule around here. I want you to repeat after me. This is important to remember. Okay? When you can do better, then you can bitch. It's the motto of the Geek Group's lab. Okay? It's a big sign hangs on the wall at the lab. When you can do better, then you can bitch. Until then, die in a fire. Please. I hate you. I hate all of you commenters who write in about how much we suck at this. We're learning this as we go along, man. I don't have a degree from Full Sail. We're science dorks with a camera. Okay, we're not professional. Yeah, anything really. I'm an idiot with a camera. So yeah. Rate, comment, subscribe. Be a part of it. Get involved. Die in a fire. We hate you all. All right, we'll see you later. Thank you.
Bye-bye. Oh, that was beautiful. I really actually like.
I'm doing great at public relations, ain't I?
I actually like the fact that it blew up.
Yeah.
That's what would have happened to the kid.
Well, go kid.
Yeah.
All right.
This video was made possible by a grant from the Future Girl Foundation.
This video was made possible by thousands of private donations from members and viewers like you. Please visit thegeekgroup.org for more information on how you can donate and become a part of our dreams of Avalon.